So, shall we start?
Yes, sir.
Is my video visible?
Yes, sir, it's visible, sir.
My video.
Yes, sir, it's visible, sir.
Okay, it's fine. Yeah, here. I just can say this. Choose the right response for the questions given below. So, yeah, the question is: consider a direct map to cache of size 32 KB with a block size 32 bytes. The CPU generate 32-bit addresses. The number of bits needed for the cache indexing and the number of tag bits are respectively. We just definitely are going to expect these questions on cache, the index and the tag, how we divide the address into index and tag. Let us recall that every time in CPU references an address, this address is going to be initially divided into index and a tag. What is index? Index is cache address. Index is cache address length. Okay. Tag is remaining. Now, there is an additional thing to be noted here is when we are provided with the block size, when there is a block size, index will be just I would say, number of bits to represent block field. Okay, I would say the middle one. Okay, now let us take the same example here. Here, what I will do is, this is total our 32-bit address size, in which initially we need to divide this into index and tag. Okay, what is index here? Index is the cache size. Initially, just go for the cache address length. What is the cache address length? Cache address length is 32 KB. 32 KB is equal to 15 digits. To represent 32 KB, we do require 15 digits. Index is equal to 15 and the tag is equal to 17. Since this is a direct mapped cache, tag will not get affected. Tag remains the same. But now since we are provided with the block portion, what is the block? Block is equal to, sorry, the word field. Initially, we need to divide again index into further subdivide into two more fields, the word field and the block field. Now, what is the word field? Word field is equal to the number of bits that takes to represent the block size. What is the block size? Block size is equal to 32 bytes. 32 bytes meaning 5 digits. So word is equal to 5 and block is equal to 10. Now, this block, this middle field will be called as index or block or line field. So you just can call this anything. Now, the number of bits for indexing and the tag digits. Indexing is 10, tag is equal to 17. So option A is correct. But most of the people, they will just get confused and they will go for 15 and 17. 15 will not be the index digits. Right after you divide the index into block and word field, the word field bits will not be a part of the indexing field. So this will be the index. Okay, the indexing field, the number of bits that are required to represent the index will just be limited to the block field. It will be 10 and 17. Is that clear?
Yes, sir.
Yeah. Now, this is take some important questions. Yeah. Yeah. Consider two cache organizations. First one is 32 KB two-way set associative with 32 byte block size. The two cache organizations. First one is a 32 KB two-way set associative with a 32 byte block size. Second one is of the same size but a direct map. Now, what is the cache? Cache size is equal to 32 KB. And there are two cache organizations. First one is 32 KB. Second one also is 32 KB, but direct map. Okay. But the first one is set associative, two-way set associative cache. Okay. And now the second one is the same thing. The size of an address is 32 bits. Address is equal to 32 bits. A 2x1 multiplexer has the latency of 0.6 nanoseconds. Latency mux is equal to latency of mux is equal to 0.6 nanoseconds. Okay, now understand here what is asked for. The hit latency of set associative organization is H1, while that of direct map cache is H2. We know that. Recall, what is the total time required to access the cache memory? Time required to access the cache memory includes three parameters. The first one is decoder latency. Okay, what is the decoder latency? Understand. The total address will be divided into three parts. The first one is the tag portion. Second one is the block portion. And the third one is a word portion. Initially, we need to locate the block. In order to locate the block, we require to have a decoder. Okay. Next, we need to compare the tag. For the comparison of the tag, to compare the tag, we require a comparator. Okay. If it is a direct map to cache, we will have decoder latency plus comparator latency. That will be your total time required to access the cache memory. Decoder latency plus comparator latency. Now, if it is a set associative map to cache, we also will be added with a multiplexer. There will be additional multiplexers required to access the cache memory, because in two-way set associative mapping, the total cache for every index there will be tag 1 word 1 block 1 and tag 2 word 2 or block 2. So to locate the first tag or the second tag, we require a multiplexer. For a two-way set associative mapped cache, we require a 2x1 multiplexer. For four-way set associative mapped cache, we require 4x1 multiplexer. But here, the important point to be understood is for a set associative mapped cache, we do require to have a multiplexer. So time required to access the cache memory is decoder latency plus comparator latency plus multiplexer latency in the case of a set associative mapped cache. If it is a direct map cache, it will be decoder latency plus comparator latency. But in the question, nothing about a decoder is specified. So decoder latency is negligible. So let us understand, let us calculate the hit latency only for set associative map to cache and a direct map to cache. Now let us go for the same procedure. You know how simply we can divide this address into index and tag. The total address size is equal to 32 bits. Okay. These 32 bits will be divided into two portions, index and a tag. What is index here? Index is the cache size. Cache size is 32 KB. Index is equal to 15 digits. Tag is equal to 17. Okay. So this is, initially we need to go for the direct map to cache. From the direct map to cache, we can go for set associative cache. Tag digits will not change in the direct map to cache, and the index bits will change. Okay, index will again be divided into block field and a word field. What is the block? First, initially, what is the word field? Initially, we need to calculate the size of a block. What is the size of the block? Size of the block here is, what is the size? 32 byte. Okay, block size is equal to 32, meaning 5 digits. So this is 5, this is 10. This is a direct mapped cache. Okay. Now, when you take set associative map to cache. When define set associative map to cache from the direct map to cache, tag digits will become 18, because in set associative map to cache, tag is equal to tag plus 1, block is equal to block minus 1. Tag bits will become 18, block bits will become 9, and the word field will not change. 18, 9, 5. Now, hit latency for set associative map to cache. Hit latency is given as, what is it? Hit latency for set associative map to cache is, decoder latency is negligible since we are not provided with comparator latency. What is the comparator latency? Comparator latency is k by 10. What is k? K is the number of tag digits here. What is the number of tag digits? 18. So 18 divided by 10 plus, there's a multiplexer here. Since we are in a set associative map to cache, multiplexer latency is 0.6. So that is 1.8 plus 0.6 is 2.4. 2.4 is the answer for the value of H1 is 2.4. The value of H1 is 2.4. H1 is what? H1 is the hit latency of set associative map to cache. Okay, direct map to cache is H2. So H1 is equal to 18 divided by 10 plus 0.6 will translate to 2.4. 2.4 is the right answer. When it comes to H2, direct map to cache. In the direct map to cache, there is no decoder, there is no multiplexer. Decoder is not given, and multiplexer will not be there in a direct map to cache. So it will just be the comparator latency. But in a direct map to cache, how many tag digits we do have? The total tag digits in the direct map to cache is equal to 17. So hit latency will be equal to hit latency H1 is equal to just the comparator latency. Okay. What is the comparator latency? K by 10. What is K? K is the number of tag digits. Okay. So K is equal to here 17. 17 divided by 10 is equal to 1.7. Okay. Is it understood? Can I go to the next question?
Yes, sir.
Yeah. Ravi?
Yes, sir.
Yeah. Okay. No. That's a wonderful question. It just looks complicated because there's a lot of too many details provided in the question, but we should be able to decode the question by reading it. First of all, before you actually get into the exam hall, first of all, understand this. You should be able to spend some time with the question to understand right after it. And see, of course, the time is limited, but unless you understand the question completely, you'll not be able to, give a thought process on the question. So first of all, I request you people to go through the question and spend some time with the question. Right after you understand the question, solution will be fairly simple. Okay. Now, let us solve this question. The CPU has 32 KB direct map to cache with a 128 byte block size. So let us get the details straight away. The cache size is 32 KB. Direct map cache, so I'm not writing anything. Block size is equal to 128 byte. Okay. Now, A is a two-dimensional array of size 512 into 512 with an element that occupy 8 bytes each. Array size is equal to 512 into 512 into 8 bytes. Okay. Total the size of the array is 512 into 512 into 8. Okay. Consider the following two C code segments, P1 and P2. Now remember this. Okay. So this is P1, one segment. This is P2, another segment. This is a program that is executing. Okay. The question is, P1 and P2 are executed independently with the same initial state, namely the array A is not in the cache, namely the array A is not in the cache and I, J, X are the registers. Let the number of cache misses experienced by P1 will be M1, that is when the block P1 is executing, we are going to get M1 misses, and when block P2 is executing, we will get the total number of misses that are termed as M2. So we need to find out M1 and M2. Now, have a look at the question carefully. If you read this question, if you read the code block, you can understand. P1 is equal to, I is equal to, P1 is, for I is equal to 0, I less than 512, I plus plus. For J is equal to 0, J less than 512, I plus plus. This is row access. Okay. Elements of the array will be accessed by row wise. Second one, P2. This is column access. X is equal to X plus A of I of J. But the second one is A of J of 5. This is the column access. This is the column access. Now, remember, during row access, total misses will be equal to total blocks. That is, in order to store our array, we require some number of blocks. Okay. For every block, there will be a miss. Total number of misses will be equal to total number of blocks. So what we need to do? We need to find out how many blocks we require to store the array. Let us go for the column misses. During the column access, total misses will be equal to total elements. This is the thumb rule. During the row access, total misses will be equal to total blocks. For every block, there will be a miss. So we need to find out how many blocks we require to store the array. For column access, how many misses we are going to encounter? We're going to come across. The total misses will be equal to the total elements of the array. See, we can directly calculate the column access because array size is directly given. Array size is 512 into 512 into 8. This is the total number of elements. 512 into 512 into 8 will be equal to 262144. Okay. So the column misses I'll directly write. Column misses will be equal to number of elements. Total array size 512 into 512 is equal to 262144. Keep it aside. Now we need to find out the number of misses for P1. When P1 is executing, how many misses that we're going to have. So the total number of misses for P1, to get that, we should be able to find out how many blocks we do require to store this array. Now simply array size is equal to into 8. This is the array size divided by a block size. What is the block size? Block size is equal to 128. If you translate this, if you simplify this, you will get, just a minute, 16384. Okay, this is equal to 16384. See, once again, during the row access, the total number of misses will be equal to total number of blocks. That's it. So we need to find out the total number of blocks. Total blocks is equal to the array size divided by one block size. That will be equal to 16384. So during the row access, M1 is the number of misses per row access, right? That is 16384. And second question is the value of M1 divided by M2. M1 divided by M2 is 16384 divided by 262144. M1 divided by M2 is 16,384 is the row misses. Column misses is 262144. If you simplify this, you will get 1 by 16. This is the answer for this. Are we clear?
Yes, sir.
Any doubts, Ravi? Ravi, do we have any doubts? Fine. Okay, next question. Simple question. Simple. Very simple. It's very similar to the previous question. Now, let us take a different type of questions. Now, consider a four-way set of of cache, which is initially empty, with a total of 16 cache blocks. Okay, we do have a total of 16 blocks. Okay, the main memory consists of 256 blocks, and the request for the memory blocks is in the following order. So, what is the detail that is given? Four-way set of cache. Initially, you can imagine if it is a direct mapped cache, cache looks like this. These are the total number of blocks. Total number of blocks is 0 to 50. But it is four-way of cache. If it is four-way of cache, total blocks will be divided into 4 sets. It looks like this. I'll put it this way. It looks like this. We'll have 4 sets. 0, 1, 2, 3. Total blocks will be divided by the associativity 16 by 4. Then we'll get number of sets. Number of sets is equal to 4. Okay. Each set is a 4 blocks because associativity is 4. Okay. Okay. 0, 1, 2, 3. This is how it looks. Okay. Now, the request for the memory blocks is in the following order. 0 to 55. These blocks are being accessed by the CPU in this order. Now, during the access, how the CPU will be able to see if a block is available in the cache memory or not. So there is a mapping rule by which the CPU will map this blocks to the cache memory. What is the mapping rule? The mapping rule is K mod C by 4. Okay. What is K? K is referenced block. Okay. C is total blocks in the cache memory. 4 is associativity. Once again, here if it is direct map to cache, it will be K mod C only. What is C? C is the total blocks. But here in the question, we have a four-way of cache. Since it is four-way, we need to divide the total blocks with 4. So it will become K mod C by 4. That becomes K mod 4. Okay. Now let us start with this. Initially, K mod 4. 0 mod 4 is equal to 0. Right? It will be placed here. Next, 255 mod 4 is equal to 3. 1 mod 4 is equal to 1. 4 mod 4 is equal to 0. 3 mod 4 is equal to 3. 8 mod 4 is equal to 0. 133 mod 4 is equal to 1. 159 mod 4 is equal to 159 mod 4 is equal to, what is 159 mod 4? Is it 1 or 3?
1, sir.
1. Okay, 216 mod 4 is equal to 0. 129 mod 4, again it is equal to 1. 63 mod 4 is equal to 3. 8 mod 4 is equal to 0. But we don't need to make any replacement because 8 is being accessed.
Sorry, sir. I
for the
think
second.
it's 3, sir. 159 mod 4.
159 is?
Mod
159
4,
is
I
3.
think
Sorry,
it's
yeah,
3.
yeah, got your point. 159 is 3. Just a minute. It is 159. This 129 comes here. $129 comes here. Yeah. So 8 is a hit and we don't need any replacement policy. Then 48. 48 also, since it is being mapped to 0, we need to go for the replacement. What is the replacement? Replacement is LRU replacement. According to LRU, least recently used block will get replaced. Out of the total blocks, 0 is the least recently used one. So 0 will be replaced by 48. Right then, 32. 32 also is being mapped to 0. For 32, what we're going to replace? We're going to replace 4. And right then, 73. Where 73 is being mapped? 73 is being mapped to 1. 92. For 92, here's the trick. Simple thing is, 92 also is being mapped to 0. And we need to have a replacement policy. But most of the people, they'll go by in this sequence, they are going to replace 8. They will end up replacing 8. But 8 cannot be replaced because when you look back, 8 is the most recently accessed one as compared to 216. Now 216 must be replaced. 216 will be replaced by 92. Then 155. 155 is going to replace 255. Okay. So what is the question? The question is, which one of the following memory block will not be in the cache memory if LRU replacement policy is used? If LRU replacement policy is used, out of 3 is available. 3 is available. Yes, 3 is available. 8 is available. Yes, 8 is available. 129 also is available. And 216 is not available. Option D is the correct option since 216 has been replaced by 92. Right? Yeah. Next question. Choose the right response for the questions below. The computer system has an L1 cache and L2 cache and a main memory unit connected as shown in figure, as shown below. The block size in the L1 cache is 4 words. The block size in the L1 cache is 4 words. Okay, block size in L2 cache is 16 words. Okay, the memory access times are 2 nanoseconds, 20 nanoseconds, and 200 nanoseconds for L1, L2, and a cache and a main memory respectively. The question is, when there is a miss in L1 and hit in L2 cache, a block gets transferred from L2 to L1. What is the time taken for this transfer? Understand? See, the total time that is required to make a transfer from L2 cache to L1 cache. Let us say CPU wants to access something, but that is not found in the L1 cache, L1 through a miss. So what CPU has to do? CPU has to search for the data item from the L2 cache. Okay, if it is available in L2, CPU needs to make a transfer from L2 to L1. So what is the total time required for this transfer? Here are several parameters to be considered here. Here, according to the figure, L1 cache block size is equal to 4 words. L2 cache block size is equal to 16 words. And there is no detail with respect to the main memory block size. Actually, the main memory, the cache level that is closer to the main memory maintain the same block size as the main memory. Here, for the main memory, to the main memory, which is the closer one, L2 is the closer one. What is the size of the L2 cache? Block size 16 words. So it is evident from the discussion what we had that the main memory block size also is equal to L2 cache block size. So main memory block size is equal to 16 words. One more time, the cache which is nearer to the main memory maintains the block size which is equal to the main memory block size. Since the L2 cache block size is equal to 16 words, main memory block size should also be equal to 16 words. But as it is getting, in a multi-level cache, the caches which are far from main memory will be maintained with a limited size of the block, limited size block, smaller block size. Okay, here the block size of the L1 cache is equal to 4 words. Now, we are asked for what is the total time required to make a transfer from L2 cache to L1 cache. Okay, so here the access times are provided. Access time of L1 cache is 2, L2 cache is 20, and main memory is 200. Now, in order to make a transfer from L2 to L1, we need to have access time of L2 and access time of L1. Transfer time is equal to access time of L2. Access time of L2 for reading. We need to get the data out. Plus access time of L1 for putting the data in. Plus transfer rate. Okay. There is a transfer rate given. There will be a transfer rate given for every time we should when we have to calculate a transfer time. But a transfer rate here is not provided. So transfer rate is negligible. So only we need to take access time of L2 and access time of L1. Access time of L2 is equal to 20 nanoseconds. Access time of L1 is 2 nanoseconds. 20 plus 2 is equal to 22 nanoseconds. This is the time required to make a transfer from L2 to L1. And there's a corresponding follow-up question, that is, if there is a miss in both L1 and L2, initially a block will get transferred from main memory to L2 and from L2 to L1. What is the total time required for this transfer? It also is very simple. Initially, we need to calculate a time transfer, that is the time required to transfer from main memory to L2. Here, main memory access time is 200 nanoseconds. L2 access time is equal to 20 nanoseconds. But it's just not 200 plus 20. Since there is a constraint on the database, since there is a restriction on the database cannot transfer the entire block. What is the size of the block? Size of the block is 16 words. We need to transfer 16 words, entire block from main memory to L2. The entire block size is equal to 16 words. But the problem is the database will not be able to accommodate total 16 words in it. At a time, the database can only make a transfer of 4 words. So the total transfer has to be divided into 4 phases, right? Total 16 words must be split into 4 phases, 4 plus 4 plus 4 plus 4. So total transfer time is equal to 4 into access time of main memory, that is 200, plus access time of L2 cache, that is 20. 4 into 220 is equal to 880 nanoseconds. This is the time required to make a transfer from main memory to L2. Plus, again, there will be a transfer from L2 to L1. L2 to L1 transfer time is equal to 22 nanoseconds, as we already calculated. 880 plus 22 is equal to 902 is the answer. Okay. This is 22 nanoseconds. L2 to L1 is 22 nanoseconds. And then when there is a miss in both L1 and L2 cache, first a block gets transferred from memory to L2, then a block gets transferred from L2 to L1 cache. The total time required for this transfer is 902 nanoseconds. Is that clear? Shall we go to the next question?
Yes, sir.
Yeah. Choose the right response for the questions given below. What is the question here? Here. This question is about tag directory, which is another important parameter in cache memory. For every cache, or a cache system in a CPU, we're going to maintain something called a tag directory. Okay. What is a tag directory? Tag directory is equal to the total tag digits. Okay. Total tag digits in the system. How do we calculate how many how many tags we'll have in a system? Equal to the number of blocks. Okay. So the number of tag digits, remember this. Number of tags in the system is equal to number of blocks. For every block, there is a tag. So number of blocks. Okay, for every block, there is a tag. Now, what is the tag directory size? Tag directory size is equal to number of blocks into one tag size. And also, you do need to remember that number of blocks will not change under any associativity, either in direct map, or in set associative mapped cache, or in four-way set associative mapped cache, or eight-way, or no matter what the associativity is, the number of tags will not change. See, for that, I'll tell you. See, in a direct mapped cache, let us say tag digits is equal to 4, block digits is equal to 4. Let us say, word digits, the number of bits, the least significant bit. What is the field? This is the word field bits will also be equal to 4. So let us say this is a direct mapped cache. In set associative, what will happen? Tag is equal to tag plus 1, 5. Block is equal to block minus 1, 3. It will remain same. Most of the people, they will think that number of blocks are reduced to 2 power 3. Earlier, these are 2 power 4. Number of blocks are reduced to 2 power 3. No. Number of blocks are not reduced to 2 power 3. Rather, the number of sets reduced to 2 power 3. And each set is of 2 blocks. That is, again, if you translate this, 2 power 3, and each block is of, 2 blocks. 2 power 3 into 2 is equal to, again, 2 power 4. Are you getting it? See, we discussed it for several times. That is, in associative mapping, the number of blocks, the bits in the middle field, that is, number of blocks will be reduced to minus 1. If it is a direct mapped cache, block is equal to block minus 1, tag is equal to tag plus 1. But actually, this is number of blocks are not reducing in the system. I will tell you. Initially, there are 4 blocks. Let us say there are 4 blocks. 0, 0, 0, 1, 1, 0, 1, 1. In set associativity, what will happen is the total number of sets, this is sets, right? This is, let us say, first block, second block, third block, and a fourth block. Number of sets only will be reduced to 2. Okay, each set is of, again, 2 blocks. So, you just need to remember this. Number of blocks will never change under no circumstances. So, here, what is the tag directory size? Number of blocks into one tag size. The rule will be applicable and remain the same for every associativity. And we also need to remember that the number of blocks would never, ever, ever, ever is going to get changed. Okay. So let us take the details. The cache size is equal to 8 KB. Okay. 8 KB require 13 digits. It's a direct mapped cache. Anyhow, it is direct mapped cache, so we don't have any problem here. Otherwise, the multiple blocks, size of the block is equal to 32 bytes. Block size is equal to 32 bytes. The process generates 32-bit addresses. So I'll put it here. Size of the address is 32. And cache size is equal to 8 KB. So initially we need to divide this index and tag into index and tag. What is index? Index is equal to the cache size. Cache size is equal to 13 bits. Okay. And remaining tag is equal to 19 digits. Index will again be divided into two more fields. That is the block field and the word field. What is the word field? Word field is equal to block size. What is the block size? Block size is equal to 32 bytes. If it is 32, we require 5 digits. So this is 5. 13 minus 5 is equal to 8, and this is 19. So the number of tag digits is equal to 19. The question is, what is the total size of the memory needed at a cache controller to store the metadata for tags? This metadata tags can also be called as a tag directory. What is the tag directory size? Tag directory size is equal to number of blocks plus one tag size. Here, within the question, we also are given that every tag is also does also contain two additional digits. For every tag, there will be two additional digits. That is one valid digit, one modified digit. So the total tag size will become 21. Okay. Total number of tag digits is equal to address tag is equal to 19 plus 2, which is equal to 21. Okay. So yeah, total 21 digits. Now, tag directory size is equal to number of blocks. What is the number of blocks? Number of blocks is 2 power 8. Into 21. What is the answer for this? 2 power 8 into 21?
5376.
5376 is the correct answer. Okay, so you just need to remember, number of blocks would never change under any circumstances. Number of blocks will remain the same as in the direct map cache. You just need to remember whenever you try to calculate the tag directory size. Next question. Do you know how to solve this? The amount of ROM needed to implement a 4-bit multiplier is simple. So very simple. Although it's a digital logic question. See, we need to implement a 4-bit multiplier. In order to maintain a 4-bit multiplier, what we need to do is we need to take a RAM. In the RAM, first 4 digits will be the multiplicand, second 4 digits will be the multiplier. And the final, for every 4 into 4, we require 80 digits, right? 1, 2, 3, 4, 5, 6, 7, 8. How many combinations we have? We'll have the combinations from 8 zeros to 8 ones. 1, 1, 1, 1, 1, 1, 1, 1. Okay. We need to put for every combination here 0, 0, 0, 0 and 0, 0, 0, 0, starting from 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1, 1, 1. So the total is 64 bits now. Just a minute. Let me calculate. Yeah. Simple. This is 2 power 4 into 2 power 4 into 8 digits, right? This is total size of the rank. This is 2 power 4. This is 2 power 4. For each, we'll have 80 digits. So 2 power 4 into 2 power 4 into 8 is equal to 2 power 4 is 2 power is equal to 3, right? 2 power 11. 2 power 11 is equal
1K.
to 2K digits,
Sorry,
right?
2K.
Do you understand completely? I just got a confusion here. This is true. It's a 80 digits. For every combination, we require 80 digits, right? Did you get my point? Balaji and Ravi, did you understand this? This is your total, multiplier. It's a 4-bit multiplier. Initially, for multiplicand, we require 2 power 4 digits. For multiplier, we also do require 2 power 4 digits. For each combination, we require 80 digits, right? So that is 2 power 4 into 2 power 4 into 8. That is equal to 2 power 11. Are we clear?
Yes, sir.
Yes,
Yeah,
sir.
that is 2K bits. This is 2K digits. This is also, we'll come back if you don't get any, which is also, cache attack directory question. I want to change. I'll put a star for this. We'll come back and solve. We do have some time. Can you quickly tell me the answer for this? Balaji and Ravi. Or should I solve? Ravi?
So we will solve, sir.
Okay.
Twenty, sir.
Hmm.
20.
Just a minute. The size of the physical address is 4 GB. 4 GB is 32. 32 cache memory size unit is 16 KB.
I got 18.
Just a minute. Let me calculate this. 32 KB minus 16 KB meaning 14, right? 32 minus 14 is equal to 18. 20. 20 is the correct answer. Should I explain?
Yes, sir.
Total 32. Index is 14. Tag is 18. Index is 14. Tag is 18. It is 4 ways associative, right? In 4 ways associative, tag is equal to tag plus 2. Index is equal to index minus 2. So this is equal to 20, right?
Yes, sir.
Yeah. 4 GB is 32. So the correct one.
So they mentioned block size of 8 and the word length of 32 bits means what we need
Still,
to do.
see, this doesn't signify anything. This is irrelevant. Block size, we need to divide. See, block size will have some significance because anyhow, since we are asked only for the tag digits, these two will be irrelevant. But anyhow, this will contribute towards, see, I'll tell you, total 32, right? From 32, initially we need to divide the total address length into index and tag. What is index here? Index is the cache size. Cache size is equal to 16 KB. 16 KB meaning 14 digits. Tag will be equal to 18, right? But again, index will further be subdivided into two more fields. One is the block field, and the next one is the word field. What's the word field? Word field is 8 words, meaning 3. So 14 minus 3 is equal to 11. So this is but I did not go for this because we are asked only for the tag digits, right?
Yes,
Is that
sir.
no? So in tag, for every associativity, one will be added. So I did not go for this. Anyhow, just need to do this practice, dividing total address into tag, index, and word field. Now this index is equal to index plus 2. Since it is 4 ways associative, block is equal to block minus 2. It will be 9. Okay. And here, the word length is equal to 32 bits. Is not going to signify anything. Here, at an address, there is a 32-bit word he is saying. We don't need the word field at all. We don't require. When we divide the instruction size into multiple fields, such as opcode, operand 1, operand 2, address, we require the word length. Do you get what I'm saying? See, for every address, there is a word. Okay, here we are talking about address. Address contains index plus tag. But we also are provided with some additional details of word size. The word size, when we take this word size into consideration, in word, what will get stored? In words, instruction will get stored. In the instruction set architecture, we also are dividing this instruction into multiple fields, such as opcode field, address 1, address 2, register. For that, we need to take this word field into account. But here, this is immaterial. This is only provided to confuse we guys, to trap we guys, to waste our time. Are we clear?
Yes, sir.
Yeah. Can you solve this? I'll give you 2 minutes. This is okay. Average memory access time. Do you know average memory access time formula? Or should I explain again?
We will solve, sir.
Will you solve or do it now?
Is it 15, sir?
Come again?
15.
14. Is the total memory access time is 50 nanoseconds. It is not 50 plus 5. If you go for 50 plus 5, you'll get 15. During a miss, total access time is equal to 50 nanoseconds. It is not given that memory access time, main memory access time is 50 nanoseconds, okay?
Okay, sir. Okay, sir.
Anyhow, let me solve this. What to do? Average memory access time is given as H1 T1 plus 1 minus H1 into T1 plus T2. Okay. What is H1 here? H1 is hit ratio, right? 0.8. T1 access time is 5 plus 1 minus H1 is 0.2. T1 plus T2 collectively is given as 50 nanoseconds. If you read the question, it is not the main memory access time. If it is separately given as the main memory access time, you need to add the cache 1 access time to the main memory access time to get the T1 plus T2. But T1 plus T2 is collectively given as 50. Read this question.
Yes, sir.
A read
Yes,
request takes 50 nanoseconds on a cache miss. That means total 50 nanoseconds contains both T1 and T2. So that is 0.8 into 5 is equal to 4 plus 0.2 into 50 is equal to 10. This is equal to 14. Otherwise, what you will get 11, right? Yes or no?
Yes,
0.2
sir.
into 55 will be 11. So 14 is the correct answer. TLB is operating systems. And tell me quickly without using pen and paper.
Eighteen, sir.
Hello?
18.
18 may be the correct answer. The 512 KB address cache size is 40. The width of the rack 512 KB meaning 19. Okay, 21. No. It cannot be. It is more than 21 because width is 40 bits. Okay, 40 will be divided into
Sir,
512
812
KB.
means,
It
sir,
is
8 setups, it means we need to add 3 bits to tag size, sir.
come again. You're not audible.
Sir, in 8-way setup associative, we need to add 3 bits for
Yes.
3 needs to.
Yes.
Then 22 I'm getting, sir.
22 is correct answer. So
Okay.
yeah, 40 bits. 40 bits will be divided into 21 plus 19. 21 plus 19. Right, 12. No. 21 plus 19, right? 512 KB meaning this is 19. This is 21. So 24 is the correct answer. Are we clear? Should I explain? Balaji, should I explain?
Sir, once explain, sir.
Sure, just a minute. That is C. Total address is equal to 40 bits. This 40 should be divided into index and tag. What is index? Index is cache size. What is the cache size? Cache size is equal to 512 KB. 512 KB takes 19 digits. Index will be equal to 19. Tag will be equal to 21. Now it is 8-way associative. If it is 8-way, tag is equal to tag plus 3, index is equal to index minus 3. Here just we don't consider the block because tag is only asked here. Tag is equal to tag plus 3, which is equal to 24. Clear?
Clear, sir.
Okay, so 24 is the correct answer. Discuss this important questions. Consider a two-level cache hierarchy. There is level 1 and there is level 2. L2. Okay. An application incurs 1.4 memory access per instruction on an average. Okay. So how many times memory access per instruction? One instruction requires 1.4 memory access. I'll give you a perspective towards this. Why for one instruction we require to have 1.4 memory access is neither 1 nor 2. How could it be 1.4 memory access? If you recall, the instructions can be one-word instructions or two-word instructions, right? We solved some questions in instruction set architecture. Some instruction takes only one word, but some instruction takes two words. Do you remember?
Yes, sir.
Some questions contains the details such as the instruction size in words, meaning some instructions will only take one word, some instruction take two words, some instruction takes some additional, maybe it just can get stored. So in order to access one instruction, how many times memory is being accessed? So on an average, memory is being accessed for 1.4 times per instruction. This is important to understand to solve this question. Okay. For this application, the miss rate of L1 is 0.1. L1 experiences 0.10% miss rate. It means 90% is the hit rate of L1. Okay. For L2, on an average, 7 misses per 1,000 instructions. So this is the thing. We are going to experience 7 misses per 1,000 instructions. Here, unit of instructions is equal to 1,000. Okay. So for 1,000 instructions, we're going to experience 7 misses. We need to calculate the miss rate of L2 corrected to 2 decimal places. Now let us understand. Initially, L1 will be accessed. See, for all the 1,000 instructions, do we directly go to L2? No. For everything, for every instruction or every data element, initially L1 cache will be searched for. Now, while you search L1 cache for the instructions, 90% of the instructions will be available in L1 cache itself. So out of 1,000, 900 instructions will be filtered out from L1 itself. You'll be able to get 900 instructions from L1. Only for the remaining 10%, that is only for the remaining 100 instructions, you're going to access L2. Okay. For 100 instructions, you're going to get 7 misses. But for one instruction, how many times memory will be accessed? For one instruction, 1.4 times memory will be accessed. So 100 into 1.4 is equal to 140. Okay. Out of 140, there will be 7 misses. So what is the rate? It is 5%. Okay. Rate is equal to 0.05. Did you get it or should I repeat once again? There are 1,000 instructions to be accessed. When you're accessing 1,000 instructions, you need to go to L1 followed by L2. L1 hit rate is 90%. That meaning out of the 1,000 instructions, 900 instructions will just be found in the L1 cache itself. Only for the remaining 100 instructions, we are going to L2. But if there are 100 instructions, we require 140 memory access because for each instruction, 1.4 times memory will be accessed because some instructions are one-word instructions, some instructions are 2 words, some instructions maybe 3 word or whatever. Now, finally, to access 100 instructions, we require 140 memory access. So miss will be considered either hit or miss will be for one memory access. There are 140 memory access and we're going to have 7 misses out of 140 memory access. 7 out of 140 is equal to 5%. When you convert it into rate, it will be 0.05. Clear? Yes or no? Balaji, Ravi?
Clear, sir.
Yeah. Ravi, you there?
Yes, sir.
Yeah. Yeah. This is another important, the topic to cover. The types of misses. This question covers types of misses. What is a miss? A miss is a miss, that is, when we don't find the data in the cache memory, this is called a miss. But anyhow, miss is a miss. But under the circumstances which occur, the miss can get classified into 3 categories. Do you remember this, Ravi?
Yes, sir.
What are those?
Conflict miss, capacity miss,
First one
and
is compulsory.
compulsory miss.
Compulsory can also be called as a cold miss, okay? Compulsory miss. Second one is a conflict miss. And the third one is a capacity miss. What is a compulsory miss? If you are searching for a data element for the first time in the cache memory, it would throw a miss. That will be categorized into compulsory miss. Second one is a conflict miss. What is a conflict miss? Due to the index conflict. See, every cache memory block will be mapped by more than one block in the main memory. Okay. So there is an index conflict. What is the conflict means? Let us say there is a X. When a data element X is being accessed for the first time, obviously it throws a compulsory miss. Right then X will be placed in the cache memory. But there is an index. This index is being shared by many of the blocks. Let us say there is one more Y, one more block Y actually is getting mapped under the same index. Now, right after X is placed under this index, when Y also gets transferred to this cache memory, Y also is getting transferred to the cache memory, X will be replaced by Y because X and Y are sharing the same index. Now, if CPU references X again, X is going to throw a conflict miss because earlier it was available. Right now, due to the conflict of the other block, X has actually been replaced. Now, when you're searching for X again, X is going to throw a conflict miss. Okay, now we'll solve this. There are 256 blocks, LRE replacement, and 256 blocks. Two ways it is set up. Okay. Total blocks will be divided by 2, and number of sets will be equal to 0 to 127. And so on. Initially, cache is empty. This is our cache memory. Initially is empty. Conflict misses are those misses occurred due to the contention of the multiple blocks for the same cache set. We know this. Compulsory misses also we know. So this is the reference, the block numbers. But this is being repeated for 10 times. We just need to calculate only the conflict misses that we're going to experience by the cache. Okay. Now, initially 0. Where 0 is getting mapped into? What is the mapping rule? Mapping rule is K mod C by 2, where K is the reference block, C is total blocks. What is 2 here? 2 is the associativity. So when you look at this, all the blocks are either getting mapped to 0 or 1. Just total blocks are the mapping is just getting limited to 0 and 1. Okay. Now 0 mod 128. 0 mod 128 is equal to 0. 128 mod 128 is equal to 0. I can place it here since there are 2 blocks under 0 set. Again 256. 256 mod 128 is equal to 0. But all these are compulsory misses. Since we are accessing these blocks for the first time, these 3 will be the compulsory misses. Then 128. 128 is a hit. We don't need to replace anything. Then comes 0. 0 is going to replace 256. Okay. And 0 is a conflict miss. Earlier, 0 was available. Due to the index contention, 0 has been replaced by 256. So when you search for 0 again, it's going to throw a conflict miss. So the first conflict miss that we're going to experience. Next thing is 128. 128 is a hit, and then followed by 256. 256 again is going to throw one more conflict miss. So 0 will be replaced by 256. The next thing is 128. Yes, 128 also is a hit. Okay, and followed by 1. 1 is being mapped to the first index, the first set. 1, and it's a compulsory miss. 129. 129 also is a compulsory miss. 257. 257 is a compulsory miss. 129. 129 is a hit, then followed by 1. 1 is going to throw a conflict miss because earlier 1 was available. Right now, when you're searching for 1, 1 actually was replaced by 257. Now 1 is going to throw a conflict miss, followed by 129. 129 is a hit, followed by 257. 257 again is going to throw a miss. So that is one more, total 4. 129 is available. So total 4 misses that we're going to get in hello, 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 hello. Yeah, tell me. చెప్పు రిజిస్టర్. లేదు, నాకు గేట్ క్లాస్ ఉన్నాయి. నేను గేట్ ట్రైనర్ కదా. నాకు సిఓఏ క్లాస్ ఉంది, నేను క్లాస్ తీసుకుంటున్నాను. సరేనా? ఓకే, ఓకే, ఉంది కానీ నాకు సాటర్డే సండే గేట్ క్లాస్ ఉంటాయి. నేను కలుద్దాంలే మళ్ళీ. సరేనా? ఓకే, బాయ్. So the total 4 misses, but this total, this is going to be repeated for 10 times. Okay, since this is being repeated for 10 times, we need to also calculate the misses for the next 9 times. But next 9 times, we'll only have the conflict misses. There will be no compulsory misses, right, Ravi? Do we have any compulsory misses in the next 9 iterations?
No, sir.
No. So we just need to calculate. See, right after the first iteration, what is available? 256, 128, 257, 129. Simple. Here, what is there? 256. Okay, so initially 0. 0 is not there. We need to replace what? 256. This 128 will not change, right? Do you understand this?
Yes.
This 128, 129 will not change. And only this 256, 257 will be changed because 128 is being repeated. Now what will happen? 0 and 256 will replace each other. Am I correct or not?
Yes, sir.
Should I repeat it? Or you got it?
Got it, sir.
Okay. So if you think sensibly, what will happen is now 256 is there and 128 is there. Now you just need to, the block reference is 0. 0 obviously is going to replace 256. Yes or no? And next is 128. 128 is the head. So what we just need to count. It's one miss. And then this is a miss. Again, this is a miss because each of the blocks are replacing each other. And this is a miss. Okay. Plus, here what is available? 1 is not available. 257 is available. So 1 and 257 are going to replace each other. So this is a miss. This is a miss. This is a miss. This is a miss. And 129 will not change. So 1, 1, 1, 1. Total 8. 4 plus, initially in the first iteration, the number of conflict misses will just be equal to 4 because in the first iteration, there will also be compulsory misses. If you filter the compulsory misses out, we got 4. But right from the next iteration, we got 8 conflict misses. 8 into 9 is equal to 8 into 9 plus, because total number of iterations is equal to 9. In the first iteration, we got 4. Right next, for each iteration, we got 8 misses, conflict misses. So 4 plus 72 is equal to 76 is the correct answer. Balaji, did you get it?
Yes, sir.
Okay. Next. Yeah. Let us solve this question. This is also one of the important questions. Generally, what is the formula for average memory access time for a two-way cache memory? Balaji or Ravi, could you please let me know? For a two-way set associative cache memory, what is the average memory access time formula?
H1 into T1 plus 1 minus H1 into T1 plus T2.
Right? That's a two-way set. 1 minus H1 into H2 into T1 plus T2 plus 1 minus H1 into 1 minus H2 into T1 plus T2 plus
T1 plus
T3.
T2
That's
plus.
a average memory access access time formula, right? But
Yes, sir.
sometimes will not be provided with what? The hit ratio. Okay, and sometimes question will not be straightforward. At that time, we have a simplified average memory access time formula. I already told it. What is it? T1 plus 1 minus H1 into T2 plus 1 minus H1 into 1 minus H2 into T2 plus T3. This is the average memory access time simplified formula. So whenever we are missing some parameters, we can directly use this formula. But you should be wisely able to pick which formula to use according to the given question. So see, this is average memory access time that we need to use here. Directly, we just plot the values. In a two-level cache system, the access times of L1 and L2 caches are 1 and 8 clock cycles respectively. The miss penalty from L2 cache to the main memory is 18 clock cycles. So that is T2 plus T3 is equal to 18 clock cycles, right? Did you get this?
Yes, sir.
Miss penalty from L2 cache to the main memory is 18 clock cycle. That includes access time of L2, access time of main memory. T2 plus T3 is equal to 18 clock cycles. The miss rate of L1 cache is twice that of L2. Here we are not provided the hit rate, rather we are provided the miss rate. The miss rate of L1 cache is twice that of L2. So what is the relationship? I just can imagine that L2 cache miss is equal to X. Then L1 miss rate will be equal to 2X. Can I say this way? Is that no?
Yes, sir.
Yeah. So L2 miss rate is equal to X, L1 miss rate is equal to 2X. Okay. Now I just can substitute the values. T1. What is T1 here? T1 is access time of L1 cache, that is 1 plus 1 minus H1. What is 1 minus H1? Miss rate of L1 cache. L1 cache miss rate is equal to 2X into access time of, sorry, T2, right? What is the T2? T2 is 8 clock cycles plus 1 minus H1. 1 minus H1 is equal to 2X. 1 minus H2 into H2 is X. 1 minus H2 is X, L2 X. And T2 plus T3. Miss penalty from L2 cache to the main memory. That is T2 plus T3. T2 plus T3 is equal to 18 clock cycles. That is equal to 1 plus 16x plus 36x square. We also can say 36x square plus 16x plus 1 is equal to 2. Because average memory access time is given as 2 cycles. Okay, so that will be simplified to 36x square plus 16x minus 1 is equal to 0. When you factorize this, you will get x as 0.056, 2x as 0.111. What is x here? X is hit rate of L2 cache. Sorry, miss rate of L2 cache. Miss rate of L1 cache is 2x. So we are asked for L1 followed by L2. L1 is 2x, L2 is x. So 0.111 and 0.056 is the correct answer. Is that clear?
Yes, sir.
Yeah. Yeah, what is the answer?
196, sir.
No. I'll explain.
Sir,
You got it.
224.
Come again?
224.
224 is the correct answer. Anyhow, I'll explain. This is so you need to calculate average memory access time separately for read and write, right? Because read and write separately is given. So initially, how many read operations we do have? Total number of read operations is equal to 160, right? Total number of read operations is equal to 160 because there are 100 instruction fish which also come under read operations, and 60. Total number of read operations is equal to total reads is equal to 160. Keep it aside. Total writes is equal to 40 on the other hand. So what we do is that is equal to, hold on, average memory access time, that is H1 T1 plus 1 minus H1 into T1 plus T2. That is equal to 1. 5 nanoseconds per read of 1 H1. What is H1? 19 nano, 0.9, right? 0.9 into 1 plus 0.1 into 5 nanoseconds read operation with a missing cache. 0.1 into, am I missing something? 1 nanosecond for a read operation for a hidden cache. Okay, 0.1 into 5. It is not 1 plus 5. So that is equal to 0.9 plus 0.5. That is equal to 1. Am I correct, Ravi?
Yes, sir.
1.4 read operations. So 1.4, it is for average read operation for one read operation, but it should be multiplied with 160. We are calculating for the program, right? So 160 into 1.4 is equal to, Ravi?
Then we need to do into 40, sir.
This is for read operation, huh?
Yes, sir. So it's a 60 only, sir.
160, 1.4 into 160. Yes or no?
Sir, 100 instruction fetch operation. 60. We need to do into 60, sir, for read operations.
No, total 160. Instruction fetch is also is the read operation, okay? Ravi, understand. Instruction fetch will get classified into which operation, sir? Total reads is equal to 160. This is the catch in the question. Although it is given as 60 memory operand read operations, but total number of read operations will be 160. Why? Because instruction fetch will also be a read operation, right?
Yes, sir.
So 160 into 1.4 is equal to what?
224, sir.
224. Okay, total access time for the read operations is equal to 224. Similarly, calculate for the write operation. Write operation is, what is H1 T1? H1 is, hit ratio is 0.9 into access time, just
392
2 nanoseconds. 0.9 into 2, right, Balaji?
Yes, sir.
Plus 0.1 into 10 for a write operation. That is equal to 1.8 plus 1. That is equal, am I correct? 2.8. 2.8 is for what? Write operation. This is one write operation. In the entire program, we have 40 write operations. 40 into 2.8 is equal to? Balaji?
56.
112, sir.
112. Okay. So the total access time for the reads is equal to 224. Total time for the entire program is 224 for read plus 112 for write. Okay, this is the total time. If you want to get average memory access time, we need to divide total time divided by total operations. Total operations is 160 plus 40 is equal to 200. Did you understand, Ravi and Balaji? This is the total access time for the reads. This is the total access time for the writes. What I have done? I have taken average memory access time for the reads. Then I multiplied this average memory access time with the reads. Then I have taken average memory access time for the writes. 2.8 is the average memory access time for one write operation. Since we are calculating for the entire program, we just multiplied with the total write operations. So this is the total read operation access time. This is the total write operation access time. But average memory access time will be total operations, sorry, the total access time divided by total operations. This is 224 plus 112 is equal to 336 by 200 is equal to 336 by 200 is equal to what?
I think it's 1.68, sir.
1.68 is the correct answer. Did you guys get this? Balaji, Ravi,
Yes, sir.
now should I repeat anything?
Clear, sir.
Well, this also will give you some perspective towards this. Let's quickly answer the question. I'll give you 1 minute to solve this. What's the answer for this?
Option C, sir.
Option is smaller blocks. Option D is the correct option. Option D is the right option. Anyhow, I will tell you. The first one will directly be ruled out because spatial locality is directly proportional to the block size. More the block size, more the spatial locality, less the block size, less the spatial locality. Are we clear?
Yes, sir.
What is the spatial locality? If you recall the locality of reference, what is locality of reference? When there is a miss, we should make a transfer from main memory to the cache memory.
Yes, sir.
But according to the locality of reference, there is a temporal locality, spatial locality. What is temporal locality? Temporal locality states that the current data element, which is not available in the cache memory, should be transferred from main memory to the cache memory for the future references. That's it. Only if it is X must get transferred. If it is Y should get transferred during a miss. But what is spatial locality? In addition to the concurrent data element that is being accessed, we also should transfer the other data items which are closer to the current data element. So in addition to the X, all the data elements that are closer to X should also be transferred to the cache memory, because right after X, obviously you're going to access the next element. If X is the current instruction, Y will be the next instruction. X is the miss right now. What will be the next miss that you're going to encounter if the Y is not present? Obviously Y, right? So spatial locality reference states that in addition to the concurrent data element that is being accessed, the other data elements which are closer to the concurrent data element should also be transferred to the cache memory. So here we need to make a transfer of an entire block where the current data element is present. So here simply, if the block size is lesser spatial locality, more better spatial locality. So the spatial locality obviously is directly proportional to the block size. So it should be ruled out. Okay? This is not right. Smaller block size implies a smaller cache. So directly ruled.
Yes,
let us go for this. I have, let us say, a 10-digit tag, 9-digit block, and 5-digit word field. Meaning, in the memory, in the cache memory, I have a 2 power 5 blocks. Sorry, I have a block size of 2 power 5 with 2 power 9 blocks. In the other words, in the cache memory, I do have 2 power 9 blocks. Each block is a 2 power 5 words. And the tag is 10. Now, the thing is, what is a smaller block size implies a smaller cache tag and hence lower cache tag overhead. Understand this. Once again, this is my total cache memory size, in which the middle field will give you the total number of blocks. If the middle field is 9 digits, total number of blocks will be equal to 2 power 9. And the least significant digit is going to signify the size of the block. Since the least significant bits is equal to 5, the total blocks is equal to 2 power 5. Here the thing is, I want to update my block size from 2 power 5 to 2 power 5. I just want to reduce my block size. Now my block size is equal to 2 power 5. I'm reducing my block size. When I reduce my block size from 2 power 5 to 2 power 4, the block field will be equal to 4. Now, when the blocks size is reduced, number of blocks will get increased, right? So at that time, I will have 2 power 10 blocks. Did you understand this or not? The total cache size is equal to 2 power 14. 9 plus 5 is equal to 2 power 14. Now what I did is, I reduced the size of the block from 2 power 5 to 2 power 4. That will affect the total number of blocks in the cache memory, right? Did you understand?
Yes, sir.
Or should I repeat? Ravi,
No,
did you
sir, it's
understand this or
clear.
not?
Yes, sir, it's clear.
It's clear, right? So when you affect the size of the block, number of blocks will get affected, but not the tag. But according to this, it is stating that a smaller block size implies smaller cache tag. How the tag size will get affected? Tag size will never get affected. When the tag size get affected, from the direct map to set associative map, if we update our cache memory, tag will be tag plus 1. If it is 2-way, tag plus 1. If it is 4-way, tag plus 2. The number of tag bits only get affected when we affect the associativity. If the associativity doesn't change, tag bits will not change at all. But here he is asserting that when there is a change in the block size, tag will also get affected. So option B will be ruled out. It is stating that a smaller block size implies smaller cache tag. He is trying to relate these two. Size of the block doesn't have any effect on the tag. So option B will be ruled out. Option C obviously will be ruled out because it also is asserting that the size of the block is having an effect on the tag. No, size of the block doesn't have an effect on the tag. I hope I made my point clear. A smaller block size incurs lower cache miss penalty. Of course, it will be true under some circumstances. Why? Because when the size of the block is small, number of blocks will increase. Total, I have, let us say, one block size is equal to, let us say, 16 words. Now I want to reduce my block to 8 only. If I reduce my block size, number of blocks will increase in the cache memory. When the number of blocks increases, obviously hit rate will also increase. So option D is correct. Are we clear?
Yes, sir.
Yeah. In the same in text, I want you people to solve this question. I have 2 minutes to solve this.
Sir, option D.
Option D. Obviously, option D is correct. Why? Because see, associativity is getting doubled. Associativity is changing. Again, take the same example of an address in which there is a word field, there is a block field, and there's a tag bit. Let us say this is 4, this is 4, and this is 4. If the associativity with the processor cache is getting doubled, let us say this is a direct map cache. There is no associativity. If it is getting double, it will become two-way set associative. In two-way set associative, what will get affected? The block field will get affected, tag field will get affected. Block is equal to block minus 1, tag is equal to tag plus 1. Okay. So when it is getting affected, what will get affected? Obviously, comparator size will get affected, right? Because earlier we had a 4-bit comparator. Now it becomes 5-bit comparator. Why comparator do we require? We do require a comparator to compare the tag digits. And then without the set index decoder, you know that we need to associate a decoder to the block field. Earlier, size of the decoder is 4 into 16. Now, since the blocks, number of block digits are reduced, size of the decoder will also reduce, right? Now, earlier we required 4 into 16. Now we do require only 3 into 8 decoder. Way selection multiplexer. Yes, we do require a multiplexer. For a direct map cache, we don't require a multiplexer. For a two-way set associative mapped cache, we require 2 into 1 multiplexer. For a four-way set associative cache, we require 4 into 1 multiplexer. Okay, obviously these three will get affected. But the width of the processor to main memory data bus size under no circumstances, whatever you change, data bus size will not change. Data bus size will be defined by the CPU size. If you get a 64-bit CPU, data bus size will be equal to 64 bits. That will never change under no circumstances. Okay, the only factor that affects the data bus size is changing your entire computer system. Okay, so under no circumstances, this option D would ever change. I'll give you one more question. Yeah, solve this. You have 3 minutes to solve this question. Will you?
Yes, sir.
Yes, sir. Option yes, sir.
Option A, 160 kilobits is correct. Should I explain?
No need, sir.
Should I, Ravi?
No need, sir.
Okay, so can I go to the next question? Did you get Ravi and Balaji both? You
Yes,
got
sir.
160, right?
Yes, sir.
Yeah. Some more questions I'll give before we go to pipelining. Next session is all about pipelining, okay? Because pipelining will because pipeline is the only topic that is left in the actual regular session. So we'll go ahead with the pipelining.
Sir, and DMA also, sir.
DMA also fine, but DMA. But next session, since we only have 2 hours, DMA will do it on Monday or Tuesday.
I think we have only classes up to 26th, sir. Sorry, today only, sir. We have classes up to today only.
I'll request them. We can have the class and some other classes, no problem. Okay.
Okay, sir. Thank you.
Okay. Anyhow, we'll also include 1 or 2 DMA that will give you a perspective towards this. This is also just wanted to be one question. It's not okay. Yeah. I'll give you 3 minutes to solve this question. Right then I'll explain. Okay. Since we are running out of the time, I will explain. Don't you try it. It's already 52. So see, this is another kind of question. It's a hypothetical question. That's why I'm pretty much interested in this hypothetical questions. It will give us a lot of different dimensions to understand. So the thing is, a CPU has a cache with a block size of 64 bytes. Cache block is equal to 64. Main memory has total main memory size is equal to where k banks, each bank is equal to c bytes. C bytes. Okay. Now, what is the total main memory size? Main memory size is C is equal to 2, K is equal to 24. That is 24 into 2. That is total 48 bytes. A rough sketch of the main memory is just like this. Okay. So this is total 0 to 23. Total 24 banks. Each bank is a 2 bytes, meaning Total 24 words. Each word is of 2 bytes. So the total main memory size is equal to 48 words. It is purely hypothetical. If you can have a look at this, the size of the cache block is 64 bytes and size of the entire main memory is just equal to 48 bytes. It is not even equal to a single block size of the cache memory. Generally, what is the scenario? The scenario of the main memory is it is much more greater and bigger than cache size. But here, one cache block is more than that of the size of the main memory. Well, consecutive C byte chunks are mapped on the consecutive banks on the wraparound. So what does actually mean? Okay, so understand. This is the cache memory. Cache memory, we have 0 to 63. He's talking about the first word will get mapped to the first word of the cache memory. And then 48 is getting mapped to the 48th word of the cache memory. And when it comes to 49th word again is getting mapped to 0th word of the cache memory. This is called a wrap around. What is given here? Consecutive C byte chunks are mapped on the consecutive banks and wrap around. So each bank is getting mapped to its respective corresponding block and so bank in the cache memory. Okay, so 0 will get mapped to 0 till 48 gets mapped to 48. When it comes to 49, 49 again gets mapped to 0. Okay, wrap around. All the K banks, when main memory is being accessed, in one access, you will be able to access all the banks since the access can be done in parallel. But two access to the same bank must be serialized. I want to access second bank for twice. But this must be serialized. Initially, we need to access second bank once, right? Then only consecutive access to the same bank can be initiated. A cache block access may involve multiple iterations of the parallel bank access depending on the amount of the data obtained by the accessing all the K banks in parallel. What does it mean? Let us say, initially, CPU wants to access a block. That block is not available in the cache memory. What will happen? During a miss in the cache memory, we need to send a block from the main memory to the cache memory. Here, cache memory block size is equal to 64. Main memory total, entire main memory size is equal to 48. So in order to make a transfer from main memory to the cache memory, we need to access main memory for many times, because even when you access the entire main memory, you will not get the total number of words which are actually sufficient to fill one block in the cache memory. So that is what it is said. A cache block access may involve multiple iterations of the parallel bank access depending on the amount of data obtained by the accessing all the K banks in parallel. Each iteration requires decoding the bank numbers to be accessed in parallel, and this takes K by 2 nanoseconds. Okay. Each iteration, when you access main memory, that requires decoding the bank numbers. These are the bank numbers. These bank numbers must be decoded. But generally, this is also hypothetical. We have no decoder for the main memory. Decoder only is applicable for the cache memory. Do you remember? Only for the cache block, we associated a decoder. Main memory will not be accessed using a decoder. But since it's a hypothetical, okay, fine. There's a main memory also requires decoder. That's main memory access time requires decoding the bank numbers plus the latency of one bank access is 80 nanoseconds. Okay, so this is the main memory access time. When you access main memory for once, you require K by 2 plus 80. Okay, so the latency of retrieving a cache block starting from the 0 address from the main memory is, that is, when you want to make a transfer from main memory to the cache memory, what is the total latency? Here, total main memory can be accessed at a time because each and every bank can be accessed in parallel. One bank access is equal to 80 nanoseconds. all the banks access will also be equal to 80 nanoseconds because all the banks can be accessed in parallel. 80 plus decoding takes k by 2 nanoseconds. Okay, so that is equal to k is equal to 24. 24 by 2 is plus 80 is equal to 92 nanoseconds to access main memory for once. When you access main memory for once, only you will be able to get 48 words. These 48 words are not sufficient enough to fill the cache memory. Here, we are trying to find out the total time required to make a transfer from main memory to the cache memory block. Now, there's a miss. A block must get transferred from main memory to the cache memory. This takes 92 nanoseconds, but in 92 nanoseconds, you'll only be able to fill 48 words. For the remaining 16 words, we need to access main memory for one more time, twice, right? So 92 into 2, which is equal to 184, is the total access time required to make a transfer from main memory to the cache memory. 184 is the correct option. Option D is the correct option. Are we clear? Yes or no? Balaji, Ravi?
Yes, sir.
Yeah. So with which we have come to an end of this session, main memory is done. And the next session, as you requested, I also will include direct memory access also. Okay?
Okay, sir.
Yeah. Session.